All right, our next speaker is Graeme Burnett. A lot of you know Graeme very well. He has 51 years of experience, particularly in the instrumentation and control with the mechatronics engineering work. The last 9 years, he's been with Swinburne University of Technology and as a consultant and the staff members as well. His current position is the Senior Test Engineer of the Smart Structure Laboratory. And the beginning of his career for 35 years, he spent his time with the Department of Defense. In between those gap of the 7 years, he's been with multiple universities in Australia as a consultant. Also, he worked with MTS customers and MTS directly at varieties of the locations in Germany, China, Japan, Mexico, US, and Australia. So he is going to give the introduction of Swinburne University hybrid simulation hardware and software. Let's welcome Graeme.
This will be the shortest presentation of the day because it's to fill in the little gap, but it's also a nice introduction and to what we physically have.
This short presentation identifies the hybrid simulation hardware and software that we have in our Smart Structures Laboratory at Swinburne. We have 3 machines capable of being used for hybrid simulation testing. Up to now, all our hybrid experience has been with our 6 degree of freedom mass facility. With this, we implement external model pseudodynamic hybrid simulation. However, we also have the capability with 2 other machines. Our FlexTest 40 1 meganewton machine could implement slow or soft pseudodynamic simulation, but we have not utilised it so far. The other rig, the wall controller, has a FlexTest 60 controller, can be used for pseudodynamic and even real-time hybrid simulation, as it is fitted with wide bandwidth actuators, and the FlexTest 60 controller is connected to our XPC target machine via ScramNet. Now, to explain all this, I need to clarify quite a lot of terminology. So in this presentation, I'll start off by identifying the basic hardware and software building blocks of an MTS control system. I'll then touch on the differences between the internal and external hybrid simulation models, and also look at 2 types of hybrid simulation implementation, the pseudodynamic and the real-time, from a hardware and a software perspective. So at the end of all of that, I can then conclude by identifying all the hybrid simulation hardware and software that we have at Swinburne. So the emphasis of this presentation is not how to do hybrid simulation, it's what you need to have to be able to carry out hybrid simulation. So let's get started. If we look at just a basic servo hydraulic system, and in this case an MTS system, at the top there is a controller PC which provides the graphic user interface to control the test. Below that we have the real-time test controller, which could be a FlexTest 40, 60 or FlexTest 100, and it is connected back to the controller PC via a 1 gigabit Ethernet connection. Now below the test controller we have 1 or more actuators. We have got all the control hardware, so we've got 1 or more actuators. Each actuator has a servo valve, a load cell and a displacement transducer. And these actuators are all fitted on the test rig and connected to the test specimen. Now, I should note that there are 3 cables between the test controller and each actuator. 1 for the servo valve, 1 for the load cell, and 1 for the displacement transducer. So in the case of our mass facility that has 8 actuators, that's 24 cables come back to the FlexTest controller. That's why it needs to be a FlexTest 60 or a FlexTest 100. Now, to be able to look at the hardware and software together, I prefer to present the diagram that we just had in a different form. I refer to it as a hardware hierarchic triangle, with the operator at the top, with the controller PC, test controller, and control hardware at the bottom, and with the test specimen at the very bottom. With this diagram, I can now extend it to be able to visualize how software maps to the hardware and how they're extended to implement the various types of hybrid testing. So now I add on the right-hand side an inverted triangle, which showing the core software components and options that complement the hardware. At the bottom of the software triangle, we have the MTS 793 core software, which is distributed both across the controller PC and the test controller. Now, the core software has three major components: the hardware interface editor, which is used to manage the locations and configuration of all the hardware; the station builder, which is used to name and customize all that hardware; and finally the station manager, which is the software item that is used to operate the system. And that includes the ability to have manual control, tuning, function generator, basic testware. These are the standard inbuilt applications. But above that, we have optional applications: test suite, multi-purpose elite, degree of freedom software, computer simulation interface, simulation models, and quite a lot more. So now with this diagram, we're in a position to see what additional hardware and software is required to implement hybrid simulation. And it is just one item of software, the hybrid simulation model options. We'll come back to that in a minute, but we also might be implementing some extra cards for communication purposes down in the hardware. Now, all the hardware and software are configured using the standard hardware interface editor and the station builder to configure it all. Although there is one extra file that we might have, an XML file that is read, that also helps configuration. Now, there are more than one types of model configuration, in fact quite a lot, but from an MTS point of view there are two software options. The two software options are the internal model and the external model, and this is an extract from one of the MTS manuals. Now, the internal model is a compiled model that runs on the controller PC and the FlexTest controller. This is a diagram that shows that, and it's mostly the internal model actually runs on the FlexTest controller. It forces the controller PC and the test controller to do a lot more work in real time. The model that's running there has to be pre-compiled to run on the controller. Swinburne haven't used this internal model options. However, our 1 meganewton universal testing machine could be used in this way. The other software option is the hybrid simulation external model, where the model runs on external hardware that communicates to the controller through a high-speed communications interface. And the simplest diagram to explain this is this, where we have a host PC where the external model is running, and we have in this case an Ethernet communication link, which is the simplest form, that carries all of the displacement command signals one way and all force feedback signals the other way. This can be referred to as soft external model hybrid simulation because of the Ethernet connection. Now, we currently don't implement this exact model purely because of the fact that our master facility requires an enormous amount more traffic. and which the Ethernet could not support. Now we have a more realistic hardware model for external model pseudodynamic testing. We've introduced an extra processor and communication hardware between the host PC and the FlexTest controller. This is the main configuration that we have at Swinburne. To overcome the communications bandwidth, the introduced processor, referred to as the real-time XPC target processor, shares a high-speed fiber optic reflective memory with the FlexTest controller that provides virtually instantaneous communications both ways. This allows the host PC to run at a lower clock rate that can be anything from 20 to 500 times slower than the 1024 Hz synchronous clock rate of the FlexTest controller. The host PC can now implement extremely complex models without having to be a supercomputer. So now let's have a closer look at the XPC target processor. Firstly, where does the name come from? For clarification, the name comes from MATLAB. It is the name for a real-time target computer that has been programmed in MATLAB Simulink, or Real-Time Workshop. The XPC target machine at Swinburne is manufactured by Speedgoat, a Swiss company that specialises in real-time hardware-in-the-loop simulation processes that work with MATLAB. The runtime executable programs are downloaded from the host PC. Now in this diagram, we can now see all of the software required to do hybrid simulation. The communications interface linking all of the computers is OpenFresco. The finite element computation that we have running on the host PC is OpenSeas. The software running in the XPC target is programmed in MATLAB on the host PC and downloaded from the host PC on the Ethernet. The software running on the FlexTest controller, as we've already referred to, is the MTS external model software. So, need a hardware interface card inside the FlexTest controller to implement the fiber optic SCRAMnet. So let's look at that. On the right here we have the actual CPU card or processor card of our controller, FlexTest controller. And to that we've added a mezzanine card to the CPU that has the reflective memory and the fiber optic interface. Now the dedicated fiber optic ring runs at 2.5 gigabit per second and it replicates the shared memory in 2 or more processors, not just a one-to-one link. So now we can come back and have a closer look. What does the software in the real-time target processor do when we're implementing pseudodynamic simulation? Let's look at the diagram with a little bit more information. In this diagram we have the host PC, the target PC and the test controller. We've got the host PC running at 2 Hz, sending commands to the Speedgoat target processor. We have the target processor sending commands at 1024 Hz to the test controller, displacement commands, and it's getting back the measured force at 1024 Hz and then sending data back at 2 Hz. to the host PC. So the role of the target processor is to interpolate between the slowly updating displacement commands from the simulation PC and to generate the external synchronous commands at 1024 Hertz. To do this, it implements what is referred to as a predictor correction function. And it is used to curve fit a predicted 1024 Hertz command. It basically fills in the gaps until the next finite element model command comes along. When that comes along, it then corrects to what it corrects its estimate, and by the end of the period, we're back on track. So this is a processor that's just running continuously throughout the whole of a simulation. Now, this is not just the only way, kind of implementation of or process that can run on the target processor. When we're doing real-time simulation, the target processor, or PC, carries out a completely different role. So this diagram, the external model is now shifted from the host PC into the real-time target processor. To do this, the FE model is simplified and pre-compiled in the host PC and downloaded to be run in real time. We intend to be able to implement this form of real-time hybrid simulation with our wall controller and test rig in the near future. And we'll be implementing it on our wall controller. Our wall controller at present is set as a FlexTest 60 controller, but we currently have two high-speed actuators, 250 kilonewton actuators, a horizontal one and a vertical one. In this particular test setup, we were testing a semi-trailer hitch, which was being loaded vertically and horizontally at different frequencies. Now, the FlexTest 60 controller supports not just two actuators, it can actually support up to 8, because that particular controller was originally being used on our mast system before we extended that to a FlexTest 100. And for that reason, the FlexTest 60 controller is also connected to the ScramNet. So we can see here now where our wall controller is hooked into the same ScramNet as the mast controller. And it's just a matter of opening a loop and putting in another controller. We could add 2 or 3 other items, data acquisition equipment, or other controllers to the loop. So we can see here now where the host PC can support either the mast or the wall controllers independently, or we could run both of them together. We can actually have other actuators pushing on items under the mast. So that brings us back to almost the start. So you can see we've talked about the hardware and software we have on our mast facility to support hybrid testing. We've seen that we don't have much experience with our 1 meganewton universal testing machine, but we also have our external model capability and real-time, as well as pseudodynamic hybrid testing capability with our wall controller, which we'll be trying out in future. So, in this presentation, I've mainly focused, as you can see, on all the electronic hardware and software needed for hybrid testing. As you can see, there's not a lot of additional hardware and software needed to be added to a standard controller. It's just a high-speed communication interface, a target PC, and a host PC. From a hardware point of view and from a software point of view, we've got the MTS internal or external model software, and then we've got OpenSeas, OpenFresco and MATLAB. So that's all the extra hardware and software needed to run a test, and that's what we've got going at present. So any questions? Yes, Alan.
How can you possibly have 51 years of experience when you're not even that old?
Seeing you've known me for about 20 years, I have changed a bit in the last 20 years.
So, realistic, a real question is, when you run the target PC and you load more and more programs onto it to run it, do you have any way to measure how much bandwidth you have left? Or is it just a surprise when the model goes all the time?
There's a lot of spare bandwidth down at that real-time target. So it's designed to in fact, we're hardly utilising its capability. And because it's a synchronous machine that can't be affected by an operating system or an update, once you get it going, it stays going.
So if it gets started, it's good?
Yes. Okay, so at this stage, if there's no further questions, we change mode. Professor Emad Gad is the Dean of Engineering of FSET. He's had a very interesting career at other universities, and we're very glad that he's here in our area. Emad is one of the people that has his finger on the pie with a lot of industries, and he's actually brought a lot of commercial work into our laboratory. A lot, we're flat out all the time, but he keeps bringing us more work. So I'd like to invite Emad.
Thank you so much for that, Graeme. I think Graeme, while he was trying to be kind to me, but he was also complaining that I am keeping him quite busy, so thank you, Graeme. On behalf of the School of Engineering, I'd certainly love to welcome you all and thank you for your participation in this event. The School of Engineering is the home of 3 departments, Civil and Construction Engineering, Mechanical and Product Design Engineering, and Aviation. So we do everything from roads and pavements to all the way to pilot training. But I often have this banter with Graeme. He says, I'm a control engineer. We deal with high precision, and indeed doing this civil stuff is sort of an old-fashioned work. So, but within the school we have all types of people. I'd certainly like to welcome all our international guests and speakers, and I'd also like to acknowledge our team here that have put this event together, particularly Riyadh, Javad, Graeme, Kevin, and Michael. So thank you very much for organizing this, and definitely our 2 partners, MTS and John Morris Group. It has been a pleasure for me to be working closely with our team here from the day one when the lab was actually opened, and then Riyadh developing the concept for hybrid testing, and then Graeme and Javad actually pushing the boundaries and making it all happen. And I'm certainly one of the beneficiaries of having such a wonderful facility on our campus. I'd hope that you'd be able to have time to network with the rest of our team, and also amongst our guests and visitors. I hope you enjoy the facilities that Graeme and has mentioned earlier, and would certainly be pleased to share information and our knowledge and our expertise that we've developed over time. The next event is actually lunch, so I shouldn't talk any more. I hope you enjoy the break, and once again, welcome to Swinburne, and I hope you enjoy the rest of the afternoon. Thank you very much.
Thank you.